Want to speed up your object whirling through our solar system is actually a nuclear-powered spacecraft sent by aliens to test how humans respond. What if an spacecraft
approaching
sent by aliens to test how humans respond?
7 visitors are approaching Earth. A headline that sounds impossible, but it's real. By late 2025, 7 sizable comets will converge on the inner solar system in just 6 months, an occurrence so rare that leading surveys like Pan-STARRS and Atlas have never logged anything close. Nestled among them is 3/Atlas, only the third interstellar comet ever detected. Its exotic chemistry and vast green coma, making it the ultimate cosmic wildcard. The odds of this happening by chance, less than 0.5% per decade. Is it just astronomical coincidence, or are we seeing something that breaks the rules of our sky? The answers and the risks start here. Every night, as the world below sleeps, a silent network of digital eyes awakens to sweep the sky. These are the world's automated comet hunters, Pan-STARRS, Atlas, and their kin. They are the tireless sentinels of the modern astronomical age. Perched atop remote sacred mountains in Hawaii, high in the arid deserts of Chile, and on the windswept plateaus of South Africa, these telescopes are positioned for unparalleled clarity. The thin, stable air at these altitudes is a window to the cosmos, far from the light-polluting haze of civilization. These instruments scan nearly the entire visible sky, night after relentless night, capturing faint, fleeting glimmers of light that would escape even the sharpest and most patient human observer. Their cameras are marvels of engineering, vast mosaics of charge-coupled devices capable of spotting objects as dim as magnitude 21. To put that in perspective, this is more than 10 million times fainter than the faintest star visible to the naked eye, and far dimmer than the dwarf planet Pluto ever appears from Earth. Each image they capture is a breathtaking tapestry, a deep field exposure containing millions of stars and distant galaxies. But within this static cosmic backdrop, the real prize is movement. The software sifts through petabytes of data, searching for a single, anomalous pixel drifting from one frame to the next. This subtle shift, almost imperceptible, is the telltale signature of a celestial wanderer, a new comet or asteroid on its journey through our solar system. The process is a relentless, high-cadence symphony of observation and computation. Pan-STARRS and Atlas operate on a schedule that covers most of the sky every 2 to 3 nights. As soon as a new set of images is captured, powerful algorithms spring into action. Their software compares each new frame against a vast, meticulously curated digital memory of the cosmos, a celestial atlas of everything that is known to be fixed. It flags anything that has moved, anything that wasn't there before. Once a promising candidate appears, a rapid-fire chain reaction begins. Automatic alerts are dispatched globally to the Minor Planet Center and a network of astronomers. This triggers a race against time, with telescopes worldwide swiveling to conduct rapid follow-up observations, aiming to confirm the discovery and calculate an initial orbit before the faint object fades back into the background noise of the cosmos. This digital vigilance has fundamentally changed the game of discovery. Just 20 years ago, discovering a comet often meant months, even years, of patient, solitary sky watching with a personal telescope, coupled with a significant dose of luck. Now, the number of confirmed finds has doubled almost every year since these surveys came online. Faint, distant visitors from the Oort cloud, which once slipped by completely unnoticed, are now routinely cataloged, tracked, and analyzed in near real time. The Minor Planet Center logs each new detection, meticulously building up a comprehensive census of these icy wanderers that grows by the hundreds annually. But for all this technological power and efficiency, even the best surveys rarely catch more than a couple of genuinely bright comets in a single season. The astonishing clustering of 7 significant comets in late 2025 is pushing the absolute limits of what these sophisticated systems were designed to handle. The engineers and operators, who are usually content to let the automated algorithms run their silent course, are now glued to their monitors. They are watching as the data pipeline lights up with more high-priority comet alerts than anyone in the field thought possible. The sheer volume of data, the overlapping observation requests, and the need to characterize each object simultaneously is a monumental task. For the very first time, the machines, these tireless digital hunters, are struggling to keep up with the sky. Before we dive deeper into this unprecedented celestial traffic jam, it pays to have a quick cheat sheet. Comet science, like any specialized field, comes with its own lexicon, but most of the key terms are more intuitive than they sound. Perihelion is perhaps the most important word in any comet forecast. It simply marks a comet's closest approach to the Sun. This is the moment of truth, the point in its orbit where the intense solar radiation does its most dramatic work, transforming a frozen, inert nucleus of ice and rock into a spectacular showpiece of gas and dust. It is at perihelion that a comet's activity peaks, its brightness soars, and its tails reach their maximum extent. For this reason, the date of perihelion is the anchor point for every prediction. Distances in the solar system become unmanageably large very quickly, so astronomers use a convenient shorthand, the astronomical unit, or AU. 1 AU is the average distance from the Earth to the Sun, approximately 93 million miles or 150 million kilometers. If you hear that a comet's perihelion is at 0.25 astronomical units, it means it will swing through a point 4 times closer to the Sun than we are, well inside the orbit of Mercury. For skywatchers, the closer a comet is to both the Sun for activity and the Earth for viewing, the better the odds for a bright display. Speaking of brightness, the magnitude scale is the astronomer's go-to system, but it works in reverse, which can be tricky. Lower numbers mean brighter objects. The Sun, for instance, is a dazzling magnitude -27. The full moon is about -12. The brightest stars are near magnitude 0 or 1. A magnitude of 6 is the absolute faintest pinprick of light most people can perceive without optical aid under pristine, dark skies. A comet that reaches a magnitude of 3 or 2 becomes a prominent object, bright enough to catch the attention of anyone stepping outside at dawn or dusk. The truly great comets, with a little luck, can even outshine the brightest stars, achieving negative magnitudes. Then there's the matter of tails. Every active comet grows at least one as it nears the Sun, and often two, each sculpted by a different force. The dust tail is the more visually common of the two. It appears broad, curved, and pale white or yellowish. It's composed of tiny grains of dust, no larger than particles of smoke, which are pushed away from the comet's nucleus by the gentle but persistent pressure of sunlight itself. These particles retain the comet's orbital momentum, so the tail curves gracefully behind the comet, tracing its path like a luminous wake. The ion tail, or gas tail, is a different beast altogether. It is typically straight, narrow, and glows with an ethereal electric blue. This tail is formed when ultraviolet sunlight strips electrons from gas molecules in the coma, a process called ionization. These newly charged particles, or ions, are then grabbed by the solar wind, a supersonic stream of charged particles constantly flowing from the Sun, and are hurled directly away from it. This means the ion tail acts like a cosmic windsock, always pointing in the direction opposite the Sun, regardless of the comet's direction of travel. Occasionally, a powerful solar storm will snap this rocket tail clean off, only for it to begin regrowing in a matter of hours. These dramatic tail disconnection events are rare, but with so many comets crowding the inner solar system, 2025 could deliver more than one, captured live on camera. Keep these basics in mind. They will help you decode every headline, every sky chart, and every spectacular surprise the 7 visitors have in store. Statisticians working with comet survey data sometimes joke that the universe is stingy with its brightest surprises. In a typical 6-month stretch, the historical averages and predictive models say we should expect 2, maybe 3 comets bright enough to be seen with backyard telescopes. The vast majority of discoveries are faint, distant objects, destined for little more than an entry in the Minor Planet Center's archives. But the lineup for late 2025 throws those sober expectations out the window. 7 significant comets, each with its perihelion packed into a single, compressed half-year, have set off alarm bells in every Monte Carlo simulation run by the world's leading comet population modelers. The numbers are stark and unambiguous. Over the last decade, digital surveys have pushed the detection rate of faint comets to unprecedented heights. Yet even with this revolutionary technology, simulations show that a cluster of 7 bright comets in one season is a profound statistical outlier. When researchers feed the real-world sensitivity of surveys like ATLAS and PanSTARRS and the best estimates of the Oort cloud's comet population into their models, the median expectation remains just 2 or 3 noteworthy comets per half-year window. The calculated probability of 7 appearing together is less than 0.5%. Some simulation runs, using more conservative assumptions, spit out odds closer to 1 in 1,000 years for a grouping of this combined brightness and proximity. This extreme rarity isn't just a product of our improved ability to see. Better cameras and more vigilant software certainly help us find more faint wanderers, but they do not conjure a septet of major visitors out of thin air. The population of large, bright comets is governed by the slow, random physics of their distant orbits in the Oort cloud and the gravitational nudges that send them plunging sunward. Improving survey efficiency is like using a finer net to catch fish. You'll catch more small ones, but it doesn't magically increase the number of whales in the ocean. The 2025 lineup stands apart from anything logged in the digital survey era, and even the old photographic records from the 20th century struggle to find a parallel. For data scientists and planetary astronomers, this is precisely the kind of anomaly that demands a second, third, and fourth look. Are we simply witnessing an astronomical royal flush? A chance alignment so improbable it feels scripted? Or could it be a sign of something more? Perhaps the aftershock of a distant collision or gravitational disturbance in the Oort cloud that sent a swarm of comets careening inward eons ago. Whatever the underlying cause, the numbers are clear. 2025's comet traffic jam is as close to winning the celestial lottery as modern astronomy has ever come. Some comets slip through the solar system almost unnoticed, their faint, ghostly glow lost against the overwhelming background of stars. Among the 7 visitors of 2025, 2 fall squarely into this quiet, unassuming category: C/2022 E2, PanSTARRS, and 240p/NEAT. They are the supporting cast, essential for the full story, but destined to remain in the shadows. C/2022 E2, PanSTARRS, reaches its perihelion on July 31st, looping in at a distant 3.82 astronomical units from the Sun. This places it well beyond the orbit of Mars, closer to Jupiter's domain, in the colder, darker suburbs of the inner solar system. At that vast distance, sunlight is a feeble force, barely capable of stirring the ancient ices on the comet's surface. The result is a modest coma, a thin, tenuous atmosphere of gas and dust, visible only through large telescopes equipped with sensitive digital detectors. For most backyard observers, it will appear as nothing more than a dim, fuzzy smudge, even on the clearest, darkest nights. 240P/NEAT is another returning traveler, a periodic comet making a familiar pass. It reaches its perihelion on December 19th at a distance of 2.12 astronomical units. While closer than Pan-STARRS, that's still more than twice as far from the Sun as Earth sits, and its modest brightness reflects this. This comet has made the journey many times before, and with each pass, it has shed some of its volatile ices, becoming dimmer and less active. It offers a low-key encore performance, a faint target for dedicated observers willing to chase it down in the cold winter sky. For both of these objects, the primary audience is not the general public, but a dedicated and passionate group of amateur astronomers. These are the citizen scientists who spend hours logging observations, meticulously stacking digital images to reveal faint details and comparing notes in online forums. Their patient, persistent work fills in the faint end of the comet census, providing crucial data points on coma size, brightness, and tail development that professional astronomers often don't have the telescope time to gather. Their contributions ensure that even the quietest visitors are counted and characterized. While these two comets won't steal the media spotlight, they remind us of the full, rich spectrum of the 2025 lineup. From these telescopic whispers to the headline-grabbing spectacles, their presence sets the stage for the brighter, more dramatic arrivals still to come. For anyone who has ever stepped outside on a clear night and wished for a comet bright enough to rival the stars, late 2025 offers more than just a faint hope. 3 of the 7 visitors, Swan, Atlas K1, and Lemon, are shaping up to be true crowd pleasers, each bringing its own unique promise of celestial spectacle. First up is SWAN, officially known as C/2025 R2. It swings in for its closest approach to Earth on October 21st, passing just a quarter of an astronomical unit away. That's a cosmic stone's throw of about 23 million miles, 37 million kilometers, close enough for the solar wind to whip up a dramatic, sweeping tail and for the comet's apparent brightness to soar. Outgassing models, based on its activity so far, predict Swan could reach a peak magnitude of 2 or 3. This level of brightness turns comet watching from a niche hobby into a neighborhood event, making it potentially visible to the naked eye even from suburban skies, a glowing dagger hanging in the pre-dawn east. Just weeks later, Atlas K1 barrels in for its perihelion on October 8th, diving deep into the solar system, well inside Mercury's orbit. The intense, unfiltered sunlight at its perihelion of 0.33 astronomical units is expected to kick its activity into overdrive. This is a trial by fire, unleashing powerful jets of gas and dust as surface ices flash vaporize under the extreme heat. Astronomers are watching for a sprawling, complex tail, and the kind of unpredictable outbursts and fragmentation events that make for breathtaking, headline-grabbing photos. Then comes Lemon, C/2025 A6, making its closest pass on November 8th at just over half an astronomical unit from the Sun. This comet is perfectly positioned for evening viewing from the northern hemisphere. Forecasts suggest it could brighten to magnitude 4, possibly even 3.5. Placing it comfortably within the range of naked eye visibility from dark locations. It will be a prime candidate for backyard binoculars, which will reveal its fuzzy coma and hint at a developing tail against the fading twilight. Each of these comets carries a different energy, a distinct personality. Swan's dramatic close approach, Atlas K1's inner orbit fireworks, and Lemon's classic, graceful evening display all offer a legitimate shot at something truly rare in a lifetime of sky watching. A comet so bright and prominent, you don't need a telescope to join the show. Not every comet in the 2025 lineup is best observed from Earth. Some, like 414P/STEREO, are practically invisible to backyard telescopes during their peak activity, yet they are positioned front and center for a dedicated fleet of robotic spacecraft stationed around the Sun. On September 27th, 414P swings just over half an astronomical unit from the Sun, closer than Venus. However, the orbital geometry from our vantage point keeps it tucked deep in the Sun's blinding glare. This is where missions like SOHO, the Solar and Heliospheric Observatory, and the twin STEREO, Solar TERRESTRIALRELATIONS Observatory, spacecraft take over. Their specialized cameras, known as coronagraphs, are designed to monitor solar storms by artificially blocking out the Sun's brilliant disk. This unique capability allows them to catch so-called sun-grazing comets as they pass through the solar corona, revealing them as bright streaks against the ethereal glow. These observations capture crucial details about a comet's activity and tail structure at the very moment of its most intense solar heating, details that ground-based observers miss entirely. Mission teams at NASA and the European Space Agency are already juggling complex schedules, weighing which of the 7 comets will receive precious instrument time. The October sky will be crowded, not just with comets, but with competing scientific priorities. SWAN and Atlas K1 promise dramatic, evolving tail displays, perfect for studying solar wind interactions. But 3I/Atlas, the interstellar newcomer, demands the closest possible scrutiny during its brief passage, as its exotic composition offers a once-in-a-generation scientific opportunity. Each spacecraft has a limited field of view and can only point at one target at a time. This necessitates tough choices. Do they focus on the rare interstellar chemistry of 3I/Atlas, or do they chase the dynamic, evolving tails of SWAN and Atlas K1 as they respond to solar storms? It's a form of scientific triage. Heliospheric imagers and coronagraphs will be tasked with tracking tail disconnection events in real time, hoping to capture the precise moment when a solar eruption severs a comet's ion tail. These observations aren't just for show, they are fundamental data. They reveal how the Sun's tangled magnetic field sculpts and interacts with cometary plasma, and by extension, with the invisible fabric of space weather that fills our entire solar system. In 2025, the fleet of solar spacecraft and the world's ground-based telescopes will form a powerful, coordinated network. Each will cover angles and wavelengths the other can't reach, working in synergy to ensure that no visitor, no matter how bright or faint, slips by unstudied. 7 comet arrivals, all squeezed into a single breathtaking calendar stretch. From late July through December 2025, the inner solar system transforms into a cosmic thoroughfare. The curtain rises in late July, with the first visitor, Pan-STARRS, making its distant quiet pass, barely stirring the detectors, a subtle prelude to the drama to come. Then, the pace quickens dramatically. By September, SWAN is rapidly closing in, its brightness climbing each morning. It is followed closely by 414P/STEREO, which slips past the Sun while the world's solar spacecraft scramble for the best vantage points. October turns into a celestial frenzy. Atlas K1 dives headlong toward the Sun, outgassing furiously as it blazes inside Mercury's orbit. Just days later, the main event, 3I/Atlas, the interstellar outlier, threads its unique hyperbolic path past Mars, its enormous green coma swelling to hundreds of thousands of kilometers across. The world's most powerful telescopes will be locked onto it, probing its alien chemistry. Lemon follows in November, drifting gracefully into the evening dusk skies, with the promise of naked-eye brightness for northern observers. Finally, in December, 240p/NEAT rounds out the sequence, a quiet encore for those dedicated astronomers still watching after a whirlwind season. When stacked on a timeline, these arrivals look less like a random scatter. When stacked on a timeline, these arrivals look less like a timeline. These arrivals look less like a random scatter and more like a cosmic cue. Each comet's perihelion falls within weeks of the next, leaving little to no downtime for astronomers or avid skywatchers. This compressed schedule means overlapping observation campaigns, crowded data pipelines at major observatories, and a steady, exhilarating stream of fresh images and data flowing to the public. For the first time in modern history, the challenge isn't finding a comet, it's keeping track of which one you're seeing on any given night. This 6-month squeeze turns the sky into a living laboratory where the fundamental mechanics of coma, tail, and solar-wind interactions play out in real time, sometimes with multiple comets visible in the same photographic frame. The stage is set for a season of tail physics and solar drama, unlike anything in recent memory. Solar storms don't just light up our polar auroras. They can turn a comet's graceful tail into a cosmic battleground. When a powerful coronal mass ejection, or CME, erupts from the sun, it hurls a billion-ton cloud of plasma and tangled magnetic fields into space at millions of miles per hour. If a comet happens to be in the crosshairs, the results can be spectacular. The ion tail, that straight electric blue blade pointing away from the sun, can be completely severed in a matter of minutes. This isn't a gradual fading or a slow unraveling. It is a sudden, violent event. One moment, the tail stretches for millions of kilometers. The next, it has been sliced clean off, left to drift in space as a ghostly, detached wisp, while the comet immediately begins to forge a fresh one. The most famous example of this was captured in April 2007, when NASA's Stereo spacecraft caught Comet Encke mid-disaster. A CME slammed into Encke's ion tail, and the spacecraft's imagers recorded it snapping away in real time. The resulting event, NASA's Stereo spacecraft caught Comet Encke mid-disaster. A CME slammed into Encke's ion tail, and the spacecraft's imagers recorded it snapping away in real time. The resulting footage became a legendary case study, replayed in Helios physics seminars and comet watcher forums alike. Scientists call the underlying mechanism magnetic reconnection, a sudden, explosive reconfiguration of magnetic field lines as the CME's field collides with the comet's. For a few hours, the comet is left in a tailless state, a stark visual signpost of the sun's invisible, far-reaching power. With 7 comets crowding the ecliptic plane in late 2025, the odds of catching another live tail snap are better than ever. The ecliptic is the flat plane where Earth and the other planets orbit, and it's also the region where CMEs are most concentrated. With so many comets clustered near this cosmic firing line, each one spends more time in the path of potential solar storms. Helios physicists and amateur astronomers alike are on high alert, watching for the telltale signs: a sudden kink, a visible break, or a ghostly wisp left behind. Each such event offers a front-row seat to the sun's awesome reach, a visceral reminder that space weather isn't just a theoretical concept. It's written across the sky in real time. The numbers coming in from the world's largest telescopes regarding 3I/Atlas are simply staggering. Astronomers using the Hubble Space Telescope and the James Webb Space Telescope, JWST, have measured the comet's coma, its glowing, extended atmosphere of gas and dust at nearly 700,000 kilometers across. That is not a typo. This single comet's atmospheric envelope is nearly half the diameter of the Sun itself and more than 50 times wider than the planet Jupiter. Images reveal a vast, diffuse greenish sphere that utterly dwarfs the tiny, rocky nucleus hidden at its heart, a fragment of another solar system lost in a cloud that could swallow planets whole. But its colossal size is only part of the story. What truly sets 3I/Atlas apart is the sheer ferocity of its activity. As sunlight strikes its surface, jets of gas and dust erupt from the nucleus with astonishing force. Measurements from JWST and ground-based observatories put the dust ejection rates at 6 kilograms per second for fine grains, about the weight of a bowling ball being blasted into space every second, and up to 60 kilograms per second for larger chunks. These powerful jets carve out distinct fans and streamers within the coma, structures that can shift and evolve from hour to hour as new vents on the rotating nucleus are exposed to the sun. The result is a living, breathing structure, constantly being reshaped by sunlight and space weather. Imaging teams at Gemini South and Palomar Observatory have spent countless nights tracking these changes, stacking long exposures to tease out the subtle, intricate details in the jets. Their work reveals a comet that is anything but static. The jets flicker and pulse, sometimes tracing out enormous arcs hundreds of thousands of kilometers long. Each new outburst adds fresh material to the coma, feeding the magnificent tales that will stretch far behind it. Even at a distance of more than 1 astronomical unit from the Sun, 3I/Atlas is putting on a show that rivals the most active comets ever observed at their peak. For astronomers, it is a rare chance to study the mechanics of cometary activity in unprecedented detail, a moving target for the most advanced instruments ever built. What happens when a comet from another star system reveals a chemistry that no one expected? Spectroscopists, working around the clock with the unparalleled capabilities of JWST, have found that 3I/Atlas is a profound rule breaker. Unlike nearly all comets from our own solar system, where water vapor dominates the show, this visitor's coma is flooded with carbon dioxide. The numbers are hard to ignore. For every 1 molecule of water detected, there are 8 molecules of CO2, an 8-to-1 ratio that sets a new record for any comet measured so far. The usual script for a bright comet says that water ice should take center stage, sublimating from a solid to a gas as sunlight hits, forming the classic glowing coma and tail. But in 3I/Atlas, water is almost an afterthought. Instead, hypervolatile CO2 ice, which vaporizes at much colder temperatures, erupts from the surface in powerful jets, painting the coma green and fueling a vibrant
Hello there, and welcome to Science for Sleep, where curiosity drifts in slowly like starlight, and science finds a softer voice at the edge of your day. Tonight we're going to wander together into one of the most astonishing frontiers of human exploration, a place so far removed from ordinary life that it can feel almost unreal. You've heard of telescopes before, of course. They sit in observatories or orbit the Earth, collecting light from planets and stars, but the one we're speaking of tonight is something altogether different. It is a window not just into distance, but into time itself. The James Webb Space Telescope, launched in the quiet darkness of December 2021, is not only peering deeper into the cosmos than any machine before it, but it is also tugging at the very threads of the universe's story. When scientists speak of a looking into deep space, they don't just mean distance, they mean history. Light doesn't travel instantly. It takes time, crossing the void year by year, century by century, until at last it brushes against a mirror or a lens. That means every time you look at the stars, you're also looking back. When you gaze at the moon, you see it as it was a little over a second ago. When you look at the sun, you're seeing light that began its journey about 8 minutes earlier. But James Webb takes this principle to an extreme. It can gather light that has been travelling not just for years or centuries, but for billions of years. So long, in fact, that the galaxies it reveals are caught in their infancy. It's easy to say that, but harder to really feel it. Imagine a camera so powerful that it could take a photograph of the Earth, and instead of showing you today's oceans and mountains, it showed you the first single-celled organisms stirring in the primordial sea. Webb isn't looking at Earth's past, but it is doing exactly that for the universe. And the most unsettling part is that what it has already shown us doesn't neatly fit the story we thought we knew. Before we step too far into what Webb has found, let me pause to ask you something personal. Where are you tonight as you listen to this? Maybe you're curled under blankets in a bedroom. Maybe you're lying on a couch with the lights low, or maybe you've put this on while travelling somewhere under a darkened sky. Whatever the case, the light from your lamp or the glow from your phone is bouncing around you in real time, but above, far past the ceiling, past the air, past the atmosphere, ancient light is still on its way. It is older than Earth itself, older than the Sun, older even than the galaxies you're familiar with. And now, thanks to James Webb, humanity can finally gather some of that ancient light and ask it questions. That's the heart of our story tonight. A telescope so sensitive, it can look to a time before the first galaxies were supposed to exist. A telescope that has already uncovered galaxies forming sooner, faster, and stranger than the standard model of cosmology ever predicted. A telescope that has made scientists wonder if our cherished timeline of the Big Bang is more flexible, more puzzling, maybe even more fragile than we once thought. Before I tell you about those discoveries, if you find this kind of journey calming, or if you feel a spark of curiosity as the night unfolds, I'd be so grateful if you left a like on this video, or perhaps subscribed. It helps bring more people into this little corner of calm exploration. And maybe it offers someone else the same restful curiosity you're feeling now. The James Webb Telescope is like no other instrument we've ever placed into the sky. It floats 1 million miles from Earth, far beyond the Moon, tucked into a stable pocket of gravity called the second Lagrange point. There it unfolds its golden mirrors, each one polished to extraordinary precision. They reflect and focus light onto instruments that aren't tuned to visible wavelengths like your eyes, but to infrared. This allows Webb to see not just what is bright in starlight, but what is hidden behind veils of dust, what is stretched out by the expansion of the cosmos, and what lies beyond the reach of ordinary telescopes. And here is where the wonder begins. Because when Webb looks far enough, it is looking to a time before stars should have had the chance to form. Yet the images it has given us show something else entirely. Galaxies shining when they should not have existed yet. Massive clusters burning brightly in an era of supposed darkness. Black holes at scales that shouldn't have been possible so soon. The very architecture of the universe seems to appear earlier than the theories predicted. It is as if Webb has peeked behind a curtain we didn't know was there, and the scene is different from the script we had rehearsed for decades. This isn't to say that the Big Bang itself is disproven, though you may have seen such bold headlines. What it does mean is that the neat, tidy version of events we were once comfortable teaching, that galaxies took hundreds of millions of years to assemble, that the first stars required long stretches of cosmic time to ignite, no longer holds so firmly. Webb has shown us that the universe was busier, faster, and perhaps more inventive than we imagined. And all of this is wrapped in a gentle paradox, because as unsettling as these findings are, they also remind us how much more there is to learn. Science is not the story of answers nailed into place, but of questions unfolding. If Webb has taught us anything already, it is that the cosmos is far more restless than our textbooks, and perhaps even more surprising than our imaginations. When people hear about the James Webb Space Telescope, they often think of it as the successor to Hubble, a newer, shinier machine meant to take prettier pictures of the cosmos, and in one sense that's true. Hubble defined a generation of astronomy. It showed us the age of the universe, captured the deep fields where thousands of galaxies crowded into a single image, and revealed planets circling distant stars. To say that Webb is merely Hubble's replacement, though, is to
I remember growing up, there was a cliche in movies and shows where if a character would die, like clockwork, they would always say, "But don't worry, they're not really gone. They still live on in your heart forever." And it's about how the character's memory and their legacy is able to transcend death, and they're alive to a certain extent because you remember them. It's metaphorical. But in reality, in the modern day and age, this idea can actually be literal. Thanks to technology! Did that scare you? Did that jump scare you? Does technology frighten you? Well, this one might. Thanks to our advances in one field in particular, AI, there are some fucking worms, some parasitic zombies out there that when someone passes away, they then get dollar signs in their eyes like Mr. Krabs because they can still get some usefulness out of them. They can parade that corpse around thanks to AI, where they can kind of like revive it with some of this like fucking forbidden necromancy so they can continue to squeeze doubloons out of their image. It's like Kabuto from Naruto, where he like revives ancient ninjas to use for his own game. Except in this way, there is no semblance of humanity left in the corpses. It is literally just these husks, these like fucking skinwalkers that just only care about money, that will use AI to bring someone back so they can continue to make money off of them even after they've died. And unfortunately, there is no one that has been exploited more, both while they were alive in their elder years and now, especially since they've passed away, than Stan Lee. And unfortunately, Stan Lee has been like this golden goose that they continue to parade around. He passed away many years ago, and since then he has been fucking minted on the blockchain as an NFT. His Twitter account was still actively being used to peddle some dog shit. He's been used in multiple like crypto projects. It goes on and on, out the wazoo. And now Los Angeles Comic-Con has announced that there is going to be an AI Stan Lee attending, where guests can pay money to get a picture with AI Stan Lee, as well as have a conversation with him. So fork over some clams and you get to interact with AI Stan Lee. Excelsior! It's exactly what he would want, I'm sure. The people that own his image now get to just continue to put him on the puppet strings and have him dance for them, where they can put whatever words in his mouth that they want. And of course he has no say-so in it because he is no longer here. He shed the mortal coil quite a long time ago, and yet since then, somehow, there are still people that are using him to make money for themselves. It's just greed. I think it is so sick and twisted. And the company that owns his likeness is trying to prop this up as like a positive thing. So the studio that owns the rights to his likeness is Cartoon Studios, and the company that developed the hologram is called Proto Hologram, and they have big plans for rapid commercial expansion of its Stan Lee IP. This was a human being, by the way, that they're now talking about like it's the fucking E3 showcase and how they're going to be like unveiling a new console here. We got big plans for Stan Lee now that he's dead, and we can do whatever we want with his likeness. Yeah, get excited. It's big moves coming from our Stan Lee IP. How is that anything but ghoulish? Oh my god. such as collectible cards and a refresh of his wax statue. Collectible cards. They're making a Stan Lee trading card game. Oh my fucking goodness. And of course, the hologram AI is part of the same push. So comic book fans can enter a special 1,500 square foot booth to interact with AI Stan Lee, who appears in the rectangular box. The AI avatar may even make a surprise appearance in other parts of the convention, such as a panel. So even when he's dead, he's still being put to work. What great news, Cartoon Studios. Wow, what saints over there. And if being trapped as an AI construct after your death for an eager audience feels a bit like something that would happen in a Marvel comic book, the folks behind the Lee avatar have already worked out a defense of the project. We'll never put words in his mouth that aren't in line with things he spoke about in his lifetime. This is according to Bob Saboni, who is the head of the Stan Lee division at Cartoon Studios. They have their own division at Cartoon Studios dedicated to figuring out ways to still use Stan Lee's image to make money off of him. Of course, with no say-so from Stan Lee, he is dead. So by the very definition, you are putting words in his mouth because he is not saying those words. He never said those words. He is not with us any longer. This is the worst goddamn defense of it you could possibly muster. No matter how you spin it, these are not his words. You can try and base it off things he said in the past, whatever, doesn't change the fact that they are still not his words and his thoughts. It's fucking crazy. They are all designed to just make money off of him. Fortunately, with decades of footage capturing his thoughts on so many subjects, we can build a voice that stays true. Not always word for word, but always faithful in spirit, context, and intent. Bull fucking loney. That is Barnack Hall. That is horseradish. The intent is just for you to make money off of Stan Lee. It's so sick, man. Holy shit. Now, there is some cases where AI, after an actor passes away, like, I can actually understand. James Earl Jones. James Earl Jones is the iconic voice of Darth Vader, and before he passed, he wanted, like, it was his desire to have his voice immortalized forever as Darth Vader. So, as I understand it, he did sign, like, the rights to his voice in AI form for Darth Vader. That is what he wanted because he always wanted to be remembered as Darth Vader. I think that's somewhat wholesome. That one I can understand. This is so far removed from that, you can't even make a good faith argument to compare the two. I tried to dig in to see if Stan Lee had ever, like, agreed to be, like, digitized post-mortem, like, we can get Bernie's through CGI or anything, because he passed away in 2018, which predates, like, the AI resurrection jutsu that we now have access to. So there's no way he could have ever agreed to that in the same way that James Earl Jones did or anything. So I was trying to see if there was anything that even, like, resembled an agreement like that. And the only thing I can find is that the people that manage Stan Lee's likeness, like his managers of the Stan Lee IP, agreed to using his likeness in media for the next, like, 20 years or something. So, like, signing over the rights to Stan Lee's likeness. But I don't know if Stan Lee was a part of that conversation. And even if he was, you have to wonder under what circumstances, because it's important to remember in the later years of Stan Lee's life, there were tons of allegations of elder abuse and manipulation with tons and tons of footage of alleged mistreatment from a lot of greedy assholes constantly looking to fucking pull money out from Stan Lee's ass every step of the way by any means necessary, come hell or high water. So I don't know for sure if he ever, like, explicitly agreed to it, and if he did he even know what he was agreeing to? Because, again, a lot of things we kept hidden from him that Stan Lee had supposedly agreed to. Others had kind of misled him, allegedly. And now that he has passed, that is still seemingly the case here, where he is just not able to rest. They have a whole division dedicated to finding ways of exploiting Stan Lee's image, apparently, at Cartoon Studios. That's... what the fuck? Like, what? How, in any way, shape, or form, could anyone possibly view this in anything other than just greedy, dystopian garbage? Just let him rest, man. I think this shit super sucks. Someone can die, and a company can just come through, buy the rights to their likeness, and then just make an AI model that can spout whatever fucking garbage it wants it to. It's so fucking shameless to me. Also, looking into it a bit more, the rights to his likeness are actually a very contentious subject. It seems like it was a messy battle about Stan Lee's image after passing. So there's a lot of meat and potatoes there, but ultimately, I guess it ended up in the hands of Cartoon Studios, who now has a whole section carved out to finding ways to milk Stan Lee's image even further, making a collectible trading card game, the AI attendance at Comic Cons. I imagine there will be another big Web3 crypto push for Stan Lee's image here, would be my guess, as part of their Stan Lee IP expansion protocol that they're excited about. I hate it. That's really about it. See ya.
This channel has had